Hello and welcome to This Explainer. Today we're diving into something that honestly feels a bit like magic. We're going to demystify how we taught a computer the literal geometry of language. We're breaking down how a massive breakthrough took words, which let's face it, are just abstract concepts to a machine, and actually gave them a physical, mathematical shape. So let's jump right in. Here's our roadmap for today. We'll start with 1, the early AI blind spot. Then 2, the company words keep. 3, building the word map. 4, the magic of math. And finally, 5, Word2Vec's modern legacy. We're going to move step by step from a pretty massive historical headache to a straight-up mathematical magic trick. Section 1. The early AI blind spot. When dog and puppy are worlds apart. Think about the word dog, and then think about the word puppy. To you and me, these words mean pretty much the exact same thing, right? But to early frequency-based AI models used before 2013, these two words were entirely separate, isolated islands of data. They had absolutely zero connection. This meant if you trained an AI classifier to understand a really positive review about a dog, it literally couldn't transfer a single ounce of that learning to a review about a puppy. Sure, you could try to patch this by manually listing out thousands of synonyms, but that completely falls apart the second you run into domain jargon, new internet slang, or foreign languages. We desperately needed a way to put dog and puppy right next to each other in a measurable space. Section 2. The company words keep. A linguistic breakthrough from 1957. Back in 1957, a linguist named J.R. Firth famously said, "You shall know a word by the company it keeps." This is a concept known as the distributional hypothesis, and it's actually really intuitive. It just means that if two words pop up in similar contexts, surrounded by the exact same types of words, they probably mean similar things. So a computer doesn't actually need to know what a dog or a puppy looks like in the real world. It just needs to notice that both of those words constantly show up next to words like bark, leash, and park. Fast forward to 2013, and researchers took that exact idea and built a 2-layer neural network called Word2Vec. Now, this came in 2 different flavors. The first architecture is called skipgram. This one looks at a center word, let's say cat, and tries to predict the surrounding context words, like the, sat, and on. The second flavor is CBOW, or continuous bag of words, which flips that completely in reverse. It looks at the context to predict the center word. The trade-off here is pretty straightforward. CBOW is faster to train, sure, but skipgram handles rare words so much better. Because of that, skipgram became the absolute standard default, the architecture that completely reshaped natural language processing for a decade. But here's the catch. Training this network was a massive mathematical headache. Trying to predict one word out of a 100,000-word vocabulary is just prohibitively expensive, computationally speaking. Enter negative sampling. This was a totally brilliant shortcut. Instead of scanning the entire dictionary to calculate all those probabilities, the model just plays a super simple yes or no binary classification game. It essentially asks, did this specific context word appear near the center word, yes or no? It compares the true correct pairing against a handful of random fake pairings, what we call the negatives. Doing this massively speeds up the whole training process. Section 3. Building the word map. From text corpus to geometric space. Okay, let's briskly walk through the 5 steps to actually build this word map. Step 1, we extract positive training pairs, so a center word and its context word straight from a giant body of text. Step 2, we initialize our embedding tables. Think of these as blank spatial maps that just assign random coordinates to words. Step 3, we train the model using that negative sampling trick we just talked about. Over millions of iterations, the model starts adjusting those coordinates. Step 4, as it trains, words that share context are quite literally nudged closer and closer together in that geometric space. And finally, step 5, once this map is fully built, it unlocks a seriously amazing analogy trick, which we are going to look at right now. Actually, scratch that. First, let's talk about the number 300. When we say geometric space, we are definitely not talking about a flat 2D map or a 3D globe. Standard pre-trained models, like the super famous Google News vectors that dropped in 2013, mapped a vocabulary of 3 million words across 300 dimensions. Now, it's virtually impossible for our human brains to visualize a 300-dimensional space, but trust me, the mathematical relationships hidden inside it are nothing short of astonishing. Section 4. The magic of math. When geometry becomes meaning. Take this famous equation. King minus man plus woman equals queen. This is where the magic really happens. If you take the 300-dimensional coordinates for the word king, you subtract the coordinates for man, and then you add the coordinates for woman, The exact point you land on in that massive 300-dimensional space is the word queen. Why does this work? Well, not because the computer suddenly understands the concept of royalty. It's because the vector of king minus man successfully isolates the mathematical direction of royal. So when you apply that royal direction to the word woman, boom, you land perfectly in the royal female region of the map. It's purely geometric, but it perfectly mirrors our human logic. Section 5, Word2Vec's modern legacy, where it wins and where it hits the wall. Word2Vec is still incredibly useful even today. For one, it's super lightweight. You can train it on highly specific domain data, like medical abstracts, in just an hour on a standard laptop. No massive GPU required. It's also highly interpretable, meaning we can plot these vectors and actually see the word clusters forming before our eyes. And really interestingly, researchers use that same analogy math we just talked about to study AI model behavior. By calculating the vector between he and she, they can create a gender axis. Then they map occupation words onto that axis to see if the AI learned biased associations from its training data. For instance, linking doctor closer to men and nurse to women. It serves as a vital, straightforward probe to figure out exactly what a model has internalized. But Word2Vec absolutely has a fatal flaw. It's often called the police see me wall. Let's think about the phrases sitting by the riverbank and depositing money at the bank. Word2Vec assigns exactly one unchanging static vector to the word bank. It literally forces the muddy side of a river and a financial institution into the exact same point in geometric space. So downstream, the classifier gets completely confused because it has no way to distinguish between two totally different meanings. Then there's the OOV, or out-of-vocabulary problem. If Word2Vec never saw a specific word in its training data, let's say some brand new slang that just popped up online, it has zero ability to represent it. It just completely fails. Later extensions, like Facebook's fastText, had to come along and fix this by breaking unknown words down into subwords and character chunks just to guess what they meant. So, to summarize this whole evolution, Word2Vec gave us static embeddings. That's one single, unchanging vector per word. It was a massive game-changing leap forward because it gave us the geometric map of language, but it fundamentally failed on words with multiple meanings. To solve that, the AI industry had to invent contextual embeddings, which are powered by modern transformers like BERT. These newer models calculate a brand new, different vector for a word every single time it appears, basing it entirely on the surrounding text in that specific sentence. Which leaves us with this final, really provocative thought. If Word2Vec permanently locked words into static points in space to give them meaning, how exactly does a modern transformer dynamically change a word's mathematical shape on the fly just by reading the sentence around it? It's a fascinating question, and honestly, cracking that puzzle is exactly what led to the massive AI revolution we are all living through right now. I hope this explainer gave you a clear map of how we first taught machines the literal shape of language. Keep learning, and I'll leave you to ponder that final question